Hi everyone, it's 10:10, so let's get started. Thank you for being here. Welcome to Breaking the Rules, Dynamic Navigation in Modularized Apps. Also unofficially known as, this talk may or may not solve all your navigation problems in 40 minutes. That's up to you though. All right, this talk is based on my experience working in heavily modularized code bases and then trying to graft navigation components on top of this. Because both of those things, navigation components and modularization, introduced scoping, which is great architecturally, but it makes things really tricky when you're trying to make navigation flows a bit more custom, a bit more dynamic. So I'll talk about how to sort of break the rules to push the limits of what navigation components can do. Also, I gave a simplified version of this talk last year, and a lot of this that was at another conference. A lot of the questions that I got were, how do you do all of this? Navigation components in a modularized architecture with compose. So today we're going to talk about how to do all of this in a compose context as well as a non-compose context. If you don't know me, my name is Sumayyah Ahmed. I've been making Android apps since 2013. I was most recently a senior engineer at Comcast in Philadelphia, but right now I'm just an Android engineer at large. Let's get started with a little context. So, one of the hallmarks of a modern Android app is a modularized architecture, and by that I mean either Gradle modules or pulling out code into independent libraries that are used at compile time. Actually, can I get a show of hands? How many people are working in a code base that's at least partially modularized right now? Yeah, that's nearly everybody. That's great for many reasons, as we all know. Everything is much more tightly scoped. Things are encapsulated, so you have very tightly controlled points of access and points of change for code. And that, of course, makes things much more testable, much more reusable. Everything is a party. What could be better? Hang on. Now that things are much more closed off, how do we navigate? In a monolithic app, we could just take it for granted that every destination is available wherever we want to go. How does that change when we're dealing with modules and with navigation components on top of that? Well, the good news is, inside a modularized enclosure, let's say inside a Gradle module, that doesn't necessarily change. You're still free to use intents or transactions, and of course now we have nav components. So we can just delegate all of that work away. We just care about access to a controller and then having the ID of our destination somewhere else. So that's great for us. The navigation logic we had to write got a lot simpler. We have to keep track of way less stuff. But we're making a big assumption here. We're assuming that this destination B is discoverable from A. We're assuming A and B exist in the same scope, which means for nav components, we're assuming they exist in the same navigation graph. That's what allows the nav controller to find B when you're in A. And that's by design, because nav components has introduced this concept of scoping. Now your navigation flows are very similar to how we think of as modules. They're supposed to be very tightly controlled, self-contained entities that are aligned around a single responsibility or a single feature set or a set of views. But that makes things tricky. So now we can't assume that every destination is available to us at compile time or runtime. Now access to these destinations is going to be an issue. That is actually part of the way nav components is designed. It's sort of assumed you're working with this single activity, multiple fragment architecture. All of your top level nav components are scoped to the activity level, very typically at the activity level. It's rare to have something else. So you have your host, which is inflated by the activity. There's your graph, typically in XML, which defines all the destinations you can get to. So if it's not in the graph, you can't get there. And your controller, which is your interface between the code that we write and the actual navigation logic, which is owned by the library. All of these elements are tightly scoped and don't easily allow access to elements outside. We have a self-contained graph in a self-contained activity in a self-contained module. How does all of this change with Compose, by the way? The answer to that is, that depends really heavily on how we've implemented Compose, what stage we're at in a Compose migration. I mean, navigation components in Compose is its whole talk by itself. But there's two cases that we can look at that will encompass most of the concerns regarding Compose. The first case is an interoperable approach to Compose, which I believe covers most people. This is the case where our activity, fragment, lifecycle owner architecture pretty much remains the same. And instead of our fragments hosting XML views, we're actually hosting composables, or possibly even a mix of composables and view layouts. As far as navigation goes, in this case, nothing really changes. All the components are still hosted by your activity. You're still defining your graphs in XML. The functionality and access of your navigation components stays the same. The fact that your fragment views are now hosting composables doesn't really change much. You're sort of operating on different layers here. The second case may change things. This is the case where you're dealing with 100% composable views. Now there's no more fragments. How does nav components work in this context? It's very likely that your setup is going to look something like this, because nav components will work with Compose in this case. Your top-level components are still there. There's your nav host, your graph, and a controller. FYI, it's now a nav host controller, but as far as developers are concerned, it's pretty much the same as a nav controller. All of these three elements are still scoped to the activity, except instead of being inflated via XML, they're just owned by a top-level composable. Again, your navigation graph is not defined in XML anymore. It's defined programmatically, but again, it also has the list of possible destinations you can get to. If your composables are not owned by that graph, you can't get there. So in all of these cases, whether you're using Compose or not, the responsibilities and the scoping around the top-level the top-level nav components remain the same. So we have the same problem. If you're in A and you're trying to get to B, but A and B exist in different scopes, let's say they're owned by different navigation graphs, which are owned by different activities, how do you do that? The graph containing A knows nothing about the graph containing B. Graphs don't know about each other's contents, with some very precise exceptions. And of course, that problem gets compounded when you're dealing with modularization. So assuming this is a highly abstracted representation of, say, 3 feature modules, all of these modules are going to have their own activities, which own their own navigation graphs. And none of these graphs know anything about each other. So how do we do navigation? How do we use the nav components library to get between these things that don't know about each other? It's kind of tricky, right? The recommended way is to actually work with the scoping. We sort of work with this built-in encapsulation, and we maintain it. It's assumed in this case, whoops, where did this go? That if you want to get from feature A to feature B, if you want to get from activity A to activity B, architecturally we're assuming that our activities and modules are designed the same way, as independent entities completely responsible for their own internal logic. So getting from A to B means A is going to launch B, and then activity B takes over. It's going to inflate its own navigation components, its own navigation graph. It'll manage everything from that point on. Activity A relinquishes control. It's essentially just handing things off. It's a handoff between activities. That's kind of what I define as static navigation. Everything is known at compile time. All destinations are defined in your XML. All possible available paths are known. That's not real life. I mean, applications are going to be very different from this. Leaving aside the fact that nobody has architecturally perfect apps, and you're probably in some halfway state between legacy code and new code, and probably partway through a Compose migration, there's going to be some tricky cases. There's a fact you're definitely going to deal with unknowns. It's possible that you don't even know where to go until something executes at runtime. What if you want to customize your navigation paths for a certain user type? So one path for user A, one path for user B. What if you want to make your navigation a little more stateful? So if you're in destination C, you want to show a different experience based on Did you get there from A to B to C versus D to E to C? How do you remember the path that you took to get to places? That's why I call this type of navigation dynamic. Now you're putting together these navigation experiences that change at runtime based on what the user's been doing. It's very tricky, but it's much more common than we think. So let's start breaking the rules. And to break down this really huge, unwieldy topic, I'm going to focus on 3 case studies. We'll look at real examples with code and how we can sort of tackle each type of problem and solve it. And we'll also do a deep dive into nav components under the hood, because once we understand how that works, breaking the rules gets a lot easier and a lot safer, and you can do more of it. The first case I found is actually quite common. You want to get from activity A to activity B, but you don't want to hand over control to activity B. You don't want that default start destination. You don't want the default navigation to take over. You want a specific, let's say, fragment B within activity B's navigation graph. But how do you do that? The developer knows we have to get to fragment B. But in your source graph, you have no access to or knowledge of the contents of the second graph. These graphs don't know anything about each other. How do we do this? Well, we're actually just talking about implicit deep links between navigation graphs. And luckily for us, Nav Components actually does support this. It's something we're really familiar with when it comes to accessing applications externally, but there is a way to build these paths between graphs, and it works across modules. So that's the first rule we're going to break. You don't have to do this handoff. You can perform your deep links directly. How does this look like in code? It's going to be a 3-step process. The first step is to make your destination deep linkable. However you've defined your destination, here we've done it the classic way in XML, your destination needs to have a deep link attribute assigned to it. The same way we would assign action or arguments attributes, we assign a deep link attribute with some unique URI. This tells the parent graph to keep track of this deep link and makes it findable and navigable from outside of this graph. So that's pretty much all we need to do on the destination side. Let's look at our source, our caller. There's a mid-step here. If your source and destination graphs, if they're in different modules, of course, we want to make sure there's a compile time dependency, and I'm putting this there because I always forget every single time. But in our source graph, it needs to have a handle on what destination we're getting to. Because remember what I said, if the destination doesn't exist in the graph, we can't get there. So typically we do this by inserting whatever fragment that we want to get to directly in the graph here. But this is not going to work because this fragment B belongs to a different graph. So remember, these graphs still don't have any access to each other's contents, even though there's a dependency between the modules. Graph 1 knows nothing about graph 2. What we can do is nest the entire destination graph inside the source graph. We'll talk about why this works in a minute, but nesting graphs is actually totally okay. It's a great way to reuse code and reuse navigation graphs we've already defined, and it is definitely necessary for deep links. So we make our destination deep linkable, we nest the destination graph inside the source graph, and the last step is just to fire the deep link. And this is pretty much the same way we call navigate with any other parameter. We just wrap that URI in a nav deep link request and pass it to the controller, and the controller takes it from there. That gets you around the problem of navigating to certain points between these encapsulated graphs. How is this going to change with Compose, though? This is all assuming our code base has no Compose in it. We talked about 2 cases earlier, so I'm going to take it case by case. The first case is the interoperable approach. This is where the architecture of our activities and fragments remains the same. The only thing that's really changed is that our fragments are hosting composables instead of XML views. In which case, surprise, deep linking remains exactly the same. If you look at this code, and we're assuming that our fragment destinations are hosting composables, that doesn't really make a difference here. Our graphs are still going to be defined in XML. The controller is still going to be owned by your top-level activity and available to all these fragment destinations. The fact that this fragment B might be hosting a composable doesn't really make a difference, which is great. It's way less work for us to do, less headache and refactor for us. The second case is a little different. That's when we're dealing with 100% composables. And now there's no more fragments, no more XML. Our activity is going to inflate these components somehow. How do we perform our deep links? Well, first, let's clarify how we are constructing these nav components in this context. And of course, this is going to look different based on the exact implementation of the code base and the style of architecture you favor. But very likely, it's going to be something like this. In our onCreate function, your activity is going to launch a composable to set up these top-level components. And as you can see here, all the three elements are there. There's your controller, which operates exactly the same way as before. There's your host, with a reference to the controller and the navigation graph. And if you're wondering, where's the graph? It's actually declared implicitly here. And as you can see, we're assigning it a couple of composable destinations. Let's talk about how to deep link in this kind of context. Same three-step process. We make our destination deep linkable. Here, in this case, I'm calling nested screen 3 composable as our deep link destination. So we assign it a deep link attribute. The syntax looks a little different, but the principle is the same. We have a unique URI and the deep link attribute. And this is just a different way, by the way, of declaring graphs. It's possible to create these graphs outside the context of the nav host, as we saw earlier. This way you can make these graphs independent of activities and accessible across activities and across multiple modules as well. But this is step one. We make our destination composable deep linkable. The second is to nest the destination graph in the source graph. And as you can see here, even implicitly declared, it's pretty simple. We just reference the graph 2 that we defined earlier. And the last step looks exactly the same as any other navigate call. We wrap the URI in a nav deep link request and hit fire. So whether you're using Compose or not, the great thing is that nav components operates on a slightly different level. Compose doesn't really change much. Deep linking is going to remain the same. The components, the functionality and access of components, of the navigation components, is going to remain largely the same. So syntactically, you may have some differences based on what type of composables you're using or what your structure of compose looks like. But luckily for us, there's not going to be a lot of refactoring involved. So we've talked a lot about that, but how does that navigation itself work? How does nav components make this happen? We're still making sure that these graphs are encapsulated. Even nested graphs are fully encapsulated. So how does the deep linking work? Let's do a deep dive into nav components. Actually, it's not too deep. We're going to do a shallow dive because it's hopefully not a lot of stuff. The first thing we care about happens at inflation time. This is when your activity is responsible for inflating your navigation components, usually somewhere around the onCreate lifecycle method. One of the first things that's going to happen is a class called NavInflator is going to find the destinations we defined. So whether they're defined in XML or they're composables defined programmatically, it's going to find your destinations and create NavDestination objects out of them. This class becomes important in a second. But for now, we just care that 3 destinations means 3 NavDestination objects, all of them added to an array belonging to your navigation graph. So even if your graph was defined in XML, at the end of the inflation process, you have a navigation graph object, which is owned by the nav controller. Your controller has a handle on the graph, as well as a handle on the backstack. And this means your controller doesn't need to care about the type of destination it is, what parameters it needs, whatever mechanism is necessary to launch it. The controller just cares about finding the correct destination and delegating control down to it itself to launch. How does that work? Every time a nav destination is created, it's going to look something like this. Most of it is information we gave it. So things like the class type, actions, arguments, deep links, what have you. This class is going to be important. That's your navigator class. It's going to be type specific based on what the destination is. So there's fragment navigators, activity, composable navigators. And this is the class that knows how to perform the actual execution of navigation. So if it's a fragment destination, the navigator is going to use transactions. If it's an activity destination, it's going to use intents. So all of this, fragments, transactions and intents haven't gone away. They're just delegated far down these layers of code. And the important thing is, nav controllers delegate control in one direction downwards to this class. This is a fully independent class. If you're a nav destination class, you're just waiting for that signal. You are that matching destination. Then it knows how to put itself on the stack, actually performing navigation. And this, by the way, is a somewhat simplified version of how navigation works, but fundamentally, this is it. Fundamentally, this is navigation in nav components, whether you're using compose or regular views or a mix of the two. Let's track what happens then when we run this code, when we ask the controller to perform navigation with a deep link request. The first thing is we extract that unique identifier, which in this case is the URI, and then the controller passes it to the graph to find a matching destination. That graph is going to iterate through the array, and in our example, we had 3 possible destinations. There's a couple of fragment destinations, and then that nested inner graph. So that it's going to try and match the URI against fragment A and fail, against fragment B and then also fail. And then we reach that nested graph. Now, it's also been through that inflation process. So it has a reference to an internal array of its own nav destinations, one of which, as we know, is the matching deep link destination we want. So it's going to take that URI identifier and parse through its own internal array and hit that match. That matching fragment in the nested graph has its own navigator class, and it knows that now it can launch and put itself on the backstack. Note that the inner graph doesn't need to share any information with the outer graph. There's no need to share information on that destination fragment or parameters or context or what have you. It's able to take that control, that URI identifier, and perform execution by itself. And this is how nav components sort of gets you around the problem of encapsulation. It makes sure that each graph or each destination is capable of launching itself. There's no need to have a back and forth with information. And of course, this makes sure that deep links don't break the encapsulation rules. Okay. Now I'm going to start contradicting myself, because I said a couple of times that if a destination doesn't exist in the graph, you can't get there. That's partly true. Destinations have to exist in the graph at runtime. You can't get there if there's no destination at runtime. However, that doesn't mean that you have to have everything defined at compile time. In between those two, we can actually mutate our graphs as needed. Nav components lets us actually change up our graphs and get a little bit more programmatic. So why would we do this? What if you don't know where to go till runtime? What if you have some sort of contract with an external module to provide content? Like say, this is our backstack, we have fragment B, and then you're supposed to get something from another module that you have no control over. So this is our graph and we're in fragment B. Let's say we receive this next fragment that we're supposed to get to at runtime. Let's say a callback executes and we've got our destination fragment. Well, we can't get there because it's not in our graph. We can't deep link to it because we have no control over this external module. And you can't hand it off to that module because they can't navigate back. You want to stay in this graph where you control the flow. Luckily for us, we can actually add and remove and change destinations from your graph on the fly. So there's no need to hand over control to something else or leave this graph if you don't want to. Let's look at a code example. So we're in our fragment B class. This, at runtime, this is our callback that executes. We've got a destination fragment class to get to, which is great. However, it does not exist in the current graph. And we can't ask the nav controller to navigate to it because it doesn't care about fragments, it cares about nav destinations. We can make one then. We can actually create a new destination at runtime via the nav controller and the navigator class. Once we've got one, we just assign it some information like a unique identifier, a label, and of course the class type that we're dealing with. And now that that destination is complete pretty much, we add it to the graph. This makes it findable and navigable from anywhere else within this graph. And that's all we need, really. We can now call navigate with the ID that we assigned earlier. We're taking advantage of the fact that the controller, again, doesn't care about what type of fragment it is, what class type, etc., in order to launch it. It just cares about delegation. Does the destination exist? Is it available in this scope? If so, I can launch it. And this is really powerful. This allows us to stitch together navigation logic on the fly, customized to our user's experience. And this, by the way, was a very simple example of like adding a single destination to the graph. It's possible now that we don't even have to have graphs look the same way each time. It's possible your graph could be completely different every time you launch an activity. This is a sample from the Android documentation page on building nav components with Kotlin DSL, which sadly is sort of out of the scope of this talk. But now it's possible to actually create entire graphs the same way we created a single destination at runtime. We can predefine a nav configuration in DSL or via API or what have you, just a creative set of IDs, and have that graph created at runtime around that configuration that you're supplied with. So it makes things much more easy when you're able to build graphs around an externally defined configuration. You don't need to have things hard-coded in your activities or your graph. The last step that we're sort of missing is data. We've talked a lot about how to perform this navigation, how to swap out views. What about communication? When you have all of these fragments or views or composables from different owners sharing the backstack, and by default it is the shared application backstack, how do they share data? Can we even do that? Why would we do that? Well, what if this is your backstack? You have a fragment B and then a deep linked fragment on top of that from another source. How do your existing fragments react to this? How does fragment B know what if they need to know what happens in this deep linked fragment? Well, they're from different navigation graphs, so they don't have a view model in common, or an activity, or a data store. The only thing they really have in common is the backstack. So that's what we're asking. How do we share data across a backstack? Nav Components wants you to use NavGraph view models, which is a very handy class and exactly what it sounds like. It's a view model scoped to a particular navigation graph. As you can see, at declaration time, you just pass it the ID of the graph you want, and you basically get a reference to this graph in any destination belonging to that graph. But does it solve our problem? Remember, in this case, that fragment B and the deep linked fragment belong to different navigation graphs. Even if they reference this line of code, the objects they get back are going to be completely different. So that doesn't work in every case. What can work is utilizing saved state handle. And if you're not familiar with this, it's part of the Android Jetpack library. It's a souped up saved instant state, essentially. It's a way to store transient data, just simple key value pairs. But Nav Components lets you access it in a really interesting way. This is our controller with a handle on the backstack. Actually, there's multiple backstacks involved, but in principle, it's going to work like this. Every time a new nav destination is added to the backstack, it's wrapped in another class called NavBackstackEntry. It's an extension on the old backstackEntry class, and it gives your destination some extra stuff. So a view model store, and very importantly, a saved state registry, which is where your saved state handle is going to survive. And it's going to be accessible to you as long as that destination is on the stack. It will have a saved state handle attached to it. Not only that, but the nav controller class exposes functions to let you see other entries on the stack. So if you have access to a nav controller, you have access to any other entry on the stack, along with their properties, including their saved state handle. So let's solve a simple problem here using saved state handle. Again, this is our backstack. Fragment B is in the foreground, and it needs to know something high level about what happens after it. Let's say it needs to know, has the user seen some new onboarding flow? It can ask the nav controller to get the current backstack entry, which is itself, get its own save state handle, and set that flag to false. Now let's say we perform our deep link, and that's the onboarding experience that we were looking for. So it can ask its nav controller to get the previous backstack entry. So even if there's separate nav controllers involved, it's pretty much the same backstack that we're operating on, usually. Get the save state handle of fragment B and set that flag to true. And then it pops itself off the stack. Once fragment B gets back to the foreground, it can try to access the latest value of that Boolean flag and react to it. Again, this is what makes navigation dynamic. You're building an in-app memory of where the user has been and what they've been doing, even when these destinations don't exist anymore. Save state handle lets you do that. And again, this was a simple application of backstack entry and save state handle, but these are really handy utilities to use, especially when it comes to composables and passing arguments to composable destinations. So that was a lot of stuff. But there are three critical things that I wanted to take away from this talk. The first is that despite navigation components, the fundamentals of Android navigation haven't really changed. We're still using tasks and the backstack and intents and flags in the same way. What has changed is, of course, access to this level of code and the responsibilities of the classes involved in nav components. Nav components adds this whole extra layer of abstraction on top, and it very tightly controls who can do what when it comes to performing navigation. So, of course, it makes things simpler for us and easier for us, less work for the developer, less control we have to manage, less state we have to manage. But understanding this is really the key to being successful in tricky environments like modules and compose and sometimes everything all at once. The good news is, though, that compose doesn't really change things much when it comes to navigation. Compose, I like to think of compose as sitting like slightly half a layer above the navigation logic. Fundamentally, compose is concerned with the rendering of UI, the management of UI state. The swapping out of these views, the navigation, is still the domain of the nav components library. So essentially, the way that we utilize this library is going to be the same in compose and outside of, like, not using compose at all. All right, thank you for sticking with me so far. Oh, thank you.